Hello and welcome to our mini lecture on chemical elements, atoms, and bonding. There are 92 elements that make up all of the matter in this world. An element is a pure substance that cannot be created or broken down by ordinary chemical means. Elements combine together to form chemical compounds which help sustain human life. You can see the elements in the human body in this diagram and table, where they are listed from the most abundant, which you can see here is oxygen, to the least abundant, magnesium, and trace elements. Compounds are substances that are formed by the joining of two or more elements. A common compound in the body is glucose, which we use to fuel our cells. Glucose is made up of carbon, hydrogen, and oxygen. An atom is the smallest quantity of an element that retains the unique properties of that element. You can have an atom of hydrogen or an atom of calcium, which would be the smallest amount of that element in existence. Atoms are made up of subatomic particles, protons, labeled P+ here in red, neutrons, labeled N0 in white, and electrons, labeled E- in blue. Protons are positively charged and neutrons have no net charge. These two particles combined give atoms their mass, while the number of protons determines the element. Electrons are negatively charged particles that spin around the nucleus where the protons and neutrons reside. Atoms have the same number of protons and electrons. Electrons circle the nucleus erratically in an electron cloud. The negative charge of the electrons is drawn to the positive charge of the protons in the nucleus, thus holding the atom together. We highly recommend that you spend some time reviewing the periodic table of elements for a better understanding of the differences between individual elements. Isotopes are different forms of the same element, but they have a different atomic weight. These occur because each isotope has a different number of neutrons while maintaining the same number of protons and electrons. Electrons tend to stay within certain regions of the electron cloud while orbiting the nucleus. It is easier to envision this through a planetary model showing electron shells. An electron shell is a layer of electrons that encircle the nucleus at a distinct energy level. The atoms of the elements found in the human body have from 1 to 5 electron shells, and all electron shells hold 8 electrons except for the first shell, which can only hold 2. The number of shells will depend on the number of electrons the atom has. In this diagram, you can see hydrogen, which only has 1 electron in the top left, and helium, which has 2 electrons. Both of these atoms have 1 electron shell, since the first shell can hold 2 electrons. All other atoms in the body have at least 2 shells, like carbon with 6 electrons down here on the left, and neon with 10 electrons and therefore having 2 full shells. The valence shell of an electron is the outermost shell. This shell is what determines how reactive the atom is. If the valence shell is full, the atom is stable and the electrons are unlikely to be pulled away from the nucleus. If the valence shell is not full, the atom is reactive and it can react with other atoms in an attempt to fill its valence shell. One example is water. Oxygen has 6 electrons in its valence shell, so it will react with 2 atoms of hydrogen to fill its valence shell, therefore creating the water molecule. Atoms come together to form molecules through chemical bonds. A bond is an electrical attraction between atoms that will hold the atoms near one another, forming molecules. Molecules are more stable than separate atoms. A chemical compound is a molecule that is made up of 2 or more atoms of different elements. There are 3 types of bonds that are important in the human body. First, we're going to look at ionic bonds. Atoms that do not have a full valence electron shell are likely to form bonds with other atoms. They will either donate or receive electrons to fill their valence shell. An atom that has an electrical charge, whether positive or negative, is called an ion. When an atom donates electrons, it becomes positively charged and is called a cation. When an atom accepts electrons, it becomes negatively charged and is called an anion. You can see that here, where sodium up at the top has donated an electron to the chlorine ion. So the sodium loses the electron and becomes positively charged. The chlorine gains the electron and then becomes negatively charged chloride. The opposite charges of cations and anions exert a strong mutual attraction that keeps atoms in close proximity, forming an ionic bond. An ionic bond is an ongoing close association between ions of opposite charges. This image at the bottom is showing you ionic bonding between sodium and chlorine. Sodium only has one electron in its valence shell. It donates that electron to chlorine to complete chlorine's valence shell. When these two atoms are bonded together, they form sodium chloride or table salt. One important note about ionic bonds is that they can be broken by water, reforming the original ions that were bonded together in the chemical compound. Most atoms exist as ions within the body for this reason. Ions are very important in the body, as you will see throughout AMP1 and AMP2. Another type of bond that is important is the covalent bond. Covalent bonds do not occur through the donation of electrons, but rather they exist when two atoms share electrons to stabilize the valence shell of both atoms. Because of this, covalent bonds are stronger than ionic bonds. This image shows multiple nonpolar covalent bonds. Single covalent bonds occur when two atoms share one pair of electrons, which you can see here between these hydrogen ions. Double covalent bonds occur when two pairs of electrons are shared, seen in the middle between two oxygen. Here. The last image at the bottom shows carbon dioxide, where there are two double covalent bonds, one between this carbon and oxygen, and the other between carbon and the other oxygen. Nonpolar molecules are molecules where the number of protons is offset by the shared number of electrons. Therefore, no area of the molecule is either positively or negatively charged. Polar covalent bonds occur when atoms bond and share electrons unequally, leaving parts of the molecule more positive and other parts more negative. An example of a polar molecule is the water molecule. Water contains one oxygen atom and two hydrogen atoms. Because the oxygen atom has 8 protons in its nucleus, and the hydrogen atoms each only have one, the negatively charged electrons are more strongly attracted to the oxygen nucleus than the hydrogen nuclei. This causes the hydrogen electrons to migrate toward the oxygen atom, which causes the oxygen end to be slightly negative, and the hydrogen end to become weakly positive. This therefore makes this a polar molecule. The last type of bond we're going to talk about today is the hydrogen bonds. Hydrogen bonds occur when a hydrogen ion that is already part of a polar molecule and therefore has a weakly positive charge is attracted to an electronegative atom from another molecule. This occurs between molecules of water, where the slightly positive hydrogen atoms are attracted to the slightly negative oxygen atoms in another water molecule. Water molecules strongly attract other types of charged molecules and ions and can dissolve those bonds. Water molecules also repel molecules with nonpolar covalent bonds, like fats, lipids, and oils. The last thing we're going to talk about today are chemical reactions. Chemical reactions begin with a reactant and end with a product, much like baking begins with ingredients and ends with a cookie or a cake. In chemical reactions, the reactants are all present in the products. No matter is created or destroyed in the process. The product will just look different than the initial reactants. The first one is a synthesis reaction. Synthesis reactions require energy to build a new product. You can see a synthesis reaction at the top where note and book are being added together to create notebook. Note and book are the reactants, and notebook is the product. This can also be written out as A plus B, and then the arrow shows that a chemical reaction is occurring, and the product is AB. Second, we have a decomposition reaction. Decomposition reactions occur when a larger molecule is broken down into smaller components. Here we see that with bookworm, where bookworm is broken down into book plus worm. In our synthesis reaction, energy was required to combine note and book, and that energy is then stored in the bonds between notebook. In a decomposition reaction, energy is released when book and worm are split apart and those bonds release the energy that they were previously holding. A decomposition reaction is AB to A plus B. Last, we have an exchange reaction. An exchange reaction includes both synthesis and decomposition, where chemical bonds are both formed and broken down, and chemical energy is absorbed, stored, and released. This is demonstrated at the bottom, where we have notebook being added to worm. So first we have notebook and worm. These are our reactants. What happens here is notebook gets broken apart in a decomposition reaction, and then book and worm get added together in a synthesis reaction. This can be delineated as AB plus C becoming A plus BC. Running out of space there. But hopefully this showed you a little bit about how these different types of chemical reactions work. Thank you so much for watching our presentation on chemical compounds, atoms, and bonding. We'll see you next time.